Welcome back to Pentagram Prime. Today's episode will focus on solving a real integral using contour integration. A few things. There were some technical issues this past week. Basically my phone broke apart. So a large portion of this episode is going to be unscripted because I am trying to get it out the door quickly before I have any further problems with my laptop. More on that in a minute. So we are going to be using something called residue theorem to solve this problem. A complete discussion of residue theorem as well as methods for calculating different types of residues will, I guess, take about an hour or so. And there are people out there far more qualified to cover that than I am. So what I'm going to do here is really just discuss my own experiences this past week working on one particular integral, and this is like I believe the most basic integral that you can work on as far as using real contour integration to solve a real integral. If you don't have experience using the complex plane or complex numbers, meaning a real number added to some multiple of the square root of -1, then you may want to stop and go and look that up. So I've noticed that most explanations of this problem seem to gloss over the part about the semicircle portion of the contour disappearing as the limit of r approaches infinity. Because basically that's what you're integrating over is a large half circle. It gets explained in the text, but something made me think that a more rigorous discussion of it would be helpful. I'm going to show you a couple of excerpts from articles I read about it on other websites. So I figured if somebody's going through this problem the first time, I should probably talk more about that portion of the integral. Now, as you can see here, my computer is really taking its time to show frames because I cannot reboot it, because the moment I reboot, I will be permanently locked out of my Google account, at least until I get a new cell phone. So yeah, I believe the part is down here. I don't know if you can see my cursor or not, but showing the part about how the one integral goes to 0 when r goes to infinity. Here we go again. So yeah, the integral is of the order of 1 over r squared, and that's why the semicircle goes to 0 when r goes to infinity. I always winced when I saw that part because I just wanted them to, explicitly throw some math and equations at me just so I could see it. So that's kind of what I'm going to try to do here. I'm a little nervous about this because I don't really have anybody to talk to and check my work. So if anybody happens to be watching this who doesn't like my approach, I'd actually love to hear from you. So I should also say right now this video is going to be very difficult to watch. It was difficult for me to produce simply because this little thing with the thing, okay, it didn't do it there, but yeah, just the way it's taken its time for me to even scroll through frames is just, it was difficult for me to deal with as I was producing this. And there goes the fan on my laptop, which means in a moment you're going to hear this buzz that is just going to try to scream over me as I try to put this thing out the door. But I got to get through this and get it uploaded, otherwise I'm not going to have anything available come Tuesday morning. So we're going to start off by showing how this integral is normally done using substitution. Oh, come on, old school approach. We're going to start by losing the bounds of infinity, or the bounds of integration. So drop those. And we're just going to focus on the integral itself. Now, if you're already familiar with how to solve this integral using standard methods of trigonometric substitution, then feel free to skip ahead, but I'm going to keep it in here for those who want it. So we're going to substitute in for x using x equal tangent of theta. We also need to substitute in for dx. So we're going to take the derivative of both sides of the substitution with respect to theta. And then we get an expression for dx in terms of d theta. In this case, dx being equal to d theta times secant squared of theta. And then we're going to employ a Pythagorean identity for secant squared of theta. As you can see here, we have components that line up on the top and the bottom. And this allows us to cancel those terms on the top and the bottom. And having done that, we get an ultra simple integral on the right hand side. And then of course we can find theta by inverting the relationship between x and theta. Now, if we recall the graph of arctangent of x, we know that the graph on both the right and the left side approaches horizontal asymptote at plus and minus x over 2. And by evaluating these limits, we find that the value is equal to pi. So now we're going to do it the hard way, or the fun way if you're like me. You're something of a numbers sadist. Now, obviously, we don't need to resort to the use of the complex numbers, or excuse me, the complex plane in order to solve this integral, but it's good practice if you're new to the subject of residues and contour integrals. That way you can see how it works on both ways. We're going to begin by replacing the bounds of integration with plus and minus r. R is a real and positive number for our purposes here. Now, just in case you're unfamiliar with what the complex plane is, this will be your wake-up call. Im of z, meaning the imaginary component of z, is not to be taken as a function of Re of z, meaning the real component of z. Z, while being distinct from your normal 2D vector, does share a lot in common with, with a 2D vector. And the plane in front of you gives us a map of where we will be integrating upon it in a 2D space. Now, any function of z will also have two components, one real and one imaginary. So you can do yourself a big favor and not try to visualize the graph of a 2D function with a 2D argument. You should not try to imagine what that looks like because it's just not happening. But it does make for very interesting speculation, when you're at the bar. But for now, we're just going to shut up and calculate. So next we will select a contour to integrate about. For this example, we will be using a half circle of radius r with the radius centered at the origin of the plane. The direction of integration about this shape will be important as we go along, so we will define it here as being counterclockwise. So the upper portions will be distinctly complex and excuse me, the upper and lower portions will be distinctly complex and real, respectively, since Im of z is 0 along the real axes. Combining these terms, we have an expression for the closed contour integral in terms of the upper and lower portions. Now, the denominator would not normally be factorable were we restricted to real numbers. But this is the complex plane, and here taking the square root of -1 is an everyday thing. In this case, I is the square root of -1. If we arrange the terms a bit, we have a complex singularity in the denominator. That seems that seems similar to something that I found on the web recently. This formula gives us a value for a contour that has a single simple singularity within it, meaning that z minus z naught must be the only factor of its kind. There are ways of dealing with higher order singularities as well as multiple poles, but we won't be dealing with them here. There are some restrictions on f of z, of course. In short, it needs to be well behaved both on and within the contour in question. No singularities, and it must be complex differentiable. The term holomorphic has some further meaning, including the relationship of the function to its own Taylor series, but we will not be concerned with the finer points today. Notice that z naught is located inside the contour in question. Applying the aforementioned formula to the closed contour in question, we are able to obtain a value for the closed contour integral. I'd like to say that here that if it seems like I'm purposely not giving a name to the mysterious formula that I just used, then you're right. It's related to something called the Cauchy integral formula, and I'm looking forward to doing a rigorous proof of it in a different episode. I also generally prefer not to use something that my audience may not completely understand. However, this episode is essentially a description of what contour integration is, why it's useful, and how it's generally performed. Basically, the introductory flight at an aviation school that you take on your first day of pilot training. There's no classroom work, not even a pre-flight inspection. You just hop in and go up so that you know why you are doing the work that comes later. Proofs can be really dry and boring things when you don't know why you're doing them. So thanks to the miracle of imaginary numbers, we have one of the three components in the above equation. If we can find one or more, then we can find the third by default. If we take the limit as r approaches infinity on both sides, we see that the left side stays basically the same since it is a constant equal to pi. Then if we look at the term to the far right, and pay close attention to our choice of variables, we see that we can get away with treating this imaginary integral as a real integral. So we can go back to using x because the integral only occurs on the real axes of the imaginary plane. And if we reinsert the limits, forgive me if this seems a bit redundant, then we have the same integral that we were originally trying to solve for. This leaves us needing to solve the middle term in order to get a value for the improper integral to the right. Okay, so I made some animation here that is going to be really choppy. Here goes. Just a big shout out to Adobe for charging $70 for what's probably a really overpriced video editing package. Or worse, forcing me to sit at the library and do this. Yep, the hits just keep on coming. So, what's really happening here as we integrate along this half circle? Obviously, we're operating at a radius of r. And since everything is happening along the same radius, a radius that we have defined as being larger than 1 in order to accommodate the value of the closed loop integral mentioned earlier. So, if we take a closer look at the value of z along c sub r, we see that the value of the integrand tends towards 1 over z squared as r gets bigger. This is because r is the dominant term in the denominator, and z is proportional to r along this contour. This is the part that I complained that I felt was kind of glossed over in a lot of treatments of this problem in other texts. So we're just going to examine this issue with this integral a little bit closer here. So if we evaluate one over z squared for infinite r, then we will get the value of the previous integral along the same path. In order to do this, we need to convert the integral from z space to theta space. Requiring both new values for z as well as dz. A term of I factors out, and we have similar terms on both the top and bottom. And I've got it in my notes here to not step on a landmine. With that said, always be aware of making sure that your terms do not go to zero before you cancel them out. I is not the only thing that factors out. And switching the sign of I theta in the denominator allows us to place the exponential in the numerator. Before we evaluate the integral, we should consider the bounds of integration for c sub r. C sub r begins at theta equal to 0, and it ends at theta equal to pi. Thus, we evaluate the antiderivative from 0 to pi. The i's factor out, and we can insert values for theta. Here we're going to employ Euler's relation for e to the negative pi. And then we just got to evaluate those terms. So the sine function cancels out, just goes to 0. Cosine is equal to -1. And then we just go to town on the algebra. So we now have an expression for the integral along c sub r in terms of r. And then, of course, if we take the limit of r as it goes to infinity, watch out, it got some more animation coming here. We find that the limit goes to 0. So, looking back at the previous 3-element equation, we see that the middle term disappears. That extra term of 1 in the denominator on the second one only makes the integrand smaller. So the fact that the other integral goes to 0 um, should make it pretty obvious. And in some ways I can see why they just put a paragraph in for that part, but I wanted to be a little more rigorous about showing that. And I think we're done here. This might be a good time to discuss my sad state of affairs. Um, Even without my cell phone dying on me and the laptop clearly not cooperating, as I'm sure anybody who's had the patience to continue watching this realizes, I'm actually spending way more time working on these videos than I should be for the quality that I'm getting. Um, so what's going to be happening is I will continue publishing weekly on Tuesday mornings, but I am not going to be doing a lesson every single week because they take way too long to prepare. So the next week or two, I'm going to do some gaming videos with Kerbal Space Program, which probably be a joy to anybody who's been watching these things who doesn't understand the math involved. But I really was hoping to push on and do some more problems. But setting up the frames and properly narrating them, it's a lot of work. In particular, it's a lot of editing. That it's becoming way more it's becoming way more longer to set up the video than it is to do the actual problem, which kind of blew my mind. So let's talk about the schedule for the next 2 weeks. Oh, I'm sorry. I forgot to edit out these frames. Oh well, yeah, same ones that were at the beginning. Let's see. There we go. Closing credits. So, um, Tuesday, June 18th, we are going to be taking off from the surface of Duna, which is Kerbal Space Program's proxy for Mars, and it'll probably take me about 20 attempts or so, but I am determined to dock with that capsule somehow or other, since I have yet to actually see anybody do it on YouTube. The week after that, I don't know how far I'm going to get with it, but I'm going to build a rocket, fire it into space, and then I'm going to maneuver a payload using ion thrusters to show the joys of very slow but very efficient acceleration, which is vital for all manner of deep space missions and actually a couple of near-Earth missions like the recent launch of the Starlink program for SpaceX. Those, I believe, are all using krypton gas as their propellant, and that's how they get to the appropriate positions in the sky. So, with all that said, thanks for watching, and this is Pentagram Prime signing off.